Hey everyone, my name is Jasper and I'm an AI researcher based in San Francisco. And today I wanted to tell you about a piece of research that I've been working on lately, specifically called forward self-models. These are small auxiliary models that I'm going to show you learn an empirical approximation of the computation of a larger neural network such as an LLM. So let's talk a bit about the motivation for this here. So in general, we're going to be looking at a specific type of neural network called the transformer, which takes data in and outputs data out and processes that data through layers that feed data in and out through the residual stream of activations. And what we're going to be specifically interested in is the interpretability question of what the model is doing in its activations or in its weights at any given layer or group of layers throughout the model. So there's a couple of existing techniques for looking at this question, such as something called probing, which is where you would look at the information that each layer in the weights makes linearly accessible to you. You can do something called ablation, which is looking at what degrades when you change something in the model, and this can tell you something about what is necessary or load-bearing for the weights. And you can look at sparse autoencoders, SAEs, which will tell you for any given definition of what a feature is, a human interpretable feature, which of them are present in the residual stream after any given layer. I think that these characterize what information exists and where it matters in the model, but none really represent a first-class representation of the computation that is actually going on in each layer. I think what's important is being able to compress that in a first-class basis and kind of look at the human readable side of that a little bit separately downstream of that. So to that end, I am going to tell you about forward self-models, which broad idea is you train a small auxiliary network to predict the model's later layer activations from its earlier layer activations. Basically, you're going to be learning what the intervening layer or layers transform their inputs over the course of the block that you're predicting. So you're going to sample the activations at an early stage and a later stage and just predict the transformation that goes on in the network in between those two things. I will show you that this captures the compressible component of the layers computation. So specifically the things that the model deems most important for recovering the layer transformation of the intervening layers is what gets captured by this forward self-model. And it also has a really interesting property of being a causally faithful and executable approximation, insofar as you can do things like swapping out the main model layers for the forward model, or you can compare what the main model computes with what the forward model computes. You'd be predicting the activations and both with the main model and the forward model, comparing those activation differences. And this is called the residual. And I'm going to show downstream that the residual, when you look at it in the context of a problem, I think it captures something called computational novelty, which is specifically what the main model computes that is kind of illegible to the forward model. So the main model computes something that is novel that maybe the forward model wouldn't have predicted the main model would think. I think that has some interesting properties, both in general and in specific problems that I'm going to tell you about. Specifically, this tracks complexity of the computation that the main model does, rather than the prediction difficulty of the main model. And this becomes important down the line. So the reason that we're interested in this sort of problem is that, broadly speaking, in order to solve any given task, I think you could probably argue that neural networks must do two things, one of which is discovering good representations that compress the data that they're dealing with, and two is performing computation with those representations, learning useful circuits. So the reason that forward self-models are interesting here is because they condition on the representations. If you recall, we're just predicting activations given other activations. And so the forward self-models really inherit the representational basis of the main model, meaning that what they need to learn is purely just a compressed basis of the computation that goes on in between, rather than needing to find their own representations of the data. And this is interesting because computation specifically does well. It works because the model is limited in its size and needs to find perform computation given the circuits that it has. Whereas representation has this interesting property of the bigger the model is, the better the representations it finds. There's a really good paper that came out recently that I'll link to in the description showing exactly why this is the case. But what this allows you to do is take the representations from the main model and compress just the computation that the main model does, which I think has some interesting properties. So here's a diagram of what the architecture of a forward self model typically looks like. On the left here, we have a simplified transformer with 4 blocks. And what we're doing is just sampling the activations at 2 given points within the model. And we will then predict, based on the earlier layer activations, we will predict the later layer activations with the forward model, such that when you then are processing data through the model, you can get to block 0, perform the forward model pass, but also perform blocks 1 through 3 passes as well. Then when you get to this A sub j point, you can then compare the forward model prediction with the main model prediction and look at the interesting properties it has there. So a bit about the architectural setup we're dealing with here. I primarily do experiments right now on a 30 million parameter GPT style model that I implemented in-house, but also I scaled these results up to running on Llama 3.2 1B and show that it has broadly the same properties here. And forward models, we're working with typically 1 to 2 or 3% of the parameters in the main model being applied to the forward model. So that's where you get your compression objective that forces the forward model to learn a compressed basis of the main model's computation. So here are results. At the smaller scale results, you can get something like 0.97 cosine similarity between the main model predicted activations and the forward model predicted activations. Over a single transformer block, we observe something like 94% recovery of the KL divergence with the forward self model if you're just replacing the main block with the forward self model block. And we're doing this with a 1% of the main model block, so something like 330K params. We can run something like causal substitution, where we substitute it and see what the degradation is. And specifically, we find that the MLP within the transformer specifically is recovered less by the forward model. So the multilayer perceptron is typically, we think of it as being the component of the transformer architecture that stores facts, rotates representational bases, that sort of thing. And we'll specifically find both at the small scale and at Llama scale that the forward self model does really well at compressing the attention heads, so the computation of the main model, while doing a bit worse on the specific like memorization, factuality, representational side of the model. So still in our small scale experiments, one thing that I found that was really interesting was the fact that you can represent the computation of the main model through a variety of different isomorphic weight representations. And by default, whenever you train this, you're typically not going to find the same weight representation that the main model has. So typically, when you train a forward model over the main model, you're going to find a completely different parameterization of the main model's computation that still does broadly the same thing. There's something called the gauge symmetry of attention. This is like a known result, and we're basically discovering each time we discover something like a new way of parameterizing the computation that the main model does. And so one really interesting finding is that the residual of the forward model we find tracks computational complexity rather than the prediction difficulty of the main model. So what does that mean? So if we look at the places that the largest errors or residuals from the forward model show up, it's the places where in stuff like delimiter tracking after an opener, stuff that requires long context attention mechanisms, really stuff where the size of the main model is being brought to bear. Whereas if you look at things like sentence start and focused attention, the places where long context is maybe less important for the main model, that's really easy, and we actually see several remarkably lower forward model residuals as a result of these sorts of positions. And interestingly, easy versus hard tokens shows almost no effect. It's not about what is easy or hard for the main model per se in terms of the probability that it would assign to a particular token. What really makes a difference is the specific architectural quirks of the main model that really rely on the main model's larger size in order to perform that computation. I found that interesting. Another interesting thing that I found is that there's graceful degradation in the KL divergence that you recover as you model larger layer gaps. So in this case, what we're doing is modeling with a given forward model, we're modeling a gap in the main model of 1, 2, and 3 layers. And you can see that both the cosine similarity between the actual and predicted activations here degrades, as well as the KL divergence that degrades. It's a really intuitive result, but I found that to be pretty interesting, that it's broadly forgiving in terms of how you want to use forward self models, and they'll kind of behave in a sensible way no matter what, even if you have some architectural differences going on. So, all right, now I'm going to talk about scaling this up to the size of Llama 3.2 1B parameters. So broadly speaking, basically the same sort of findings end up showing up. We have 0.97 or 0.93 cosine similarity between the actual and predicted activations this time over a single layer gap. And this time we see 74% KL recovery. In general, my feeling is that this is probably due to the fact that Llama has more MLP weight than our toy model. So in general, these things are just going to kind of vary based on architectural differences. But we see the same effects in terms of both causal substitution, in terms of you can substitute the forward model for the main model layers and get broadly the same results. We also see uniform degradation across the board on the sorts of places where KL and cosine get worse. So it's not like when you substitute it, there's this one like category of data that gets worse. It just kind of gets worse across the board. And this makes sense because ultimately what we're doing is modeling the layer as a whole and learning empirically what matters the most for that transformation that layer entails. So one other interesting finding is that on Llama 3.2 1B, the forward self model specifically learns a basis for the 32 attention heads in the main model that is about equally as well as anything else. It learns all of the attention heads equally, and there's dramatically more error that maps onto the MLP than the attention heads, which is, again, what we saw before. But it really goes to show you that for the things that are really kind of doing the bulk of the computation in the main model, even a really small forward model can capture that pretty effectively. What ends up being missed is the rotational and memorizational capacity of the MLP, which is definitely important, but from a computational perspective is not really what we think of as kind of the core of computation. It's rotating the representations into a basis where the computation can take place. So I found that interesting. So let's discuss what this means and why I think this is important. So again, this is an empirical approximation of any number of layers in the main model that you can then do any number of things with, including showing those predictions to the main model itself. You can look at the way that the errors map onto data. And you can even potentially look at this as a sort of generalization machine where you could look at empirically what the forward model finds most generalizable across the main model. Really, there's a lot of exciting directions I think this can go. So why is this the case? This is specifically because, again, we're looking at a neural network in the main model that has to do two tasks of discovering representations and performing computation with those representations. And again, one thing we found interesting in a lot of literature is that the reason that the models learn circuits at all, as opposed to memorizing all mappings between input and output data, is because of that capacity limitation relative to the complexity of the data that is being modeled. So with a model that is dramatically too big and data that is dramatically too small, there's really no intrinsic reason for the model to learn anything at all in the sense that we would consider learning. But when you start making the data bigger and the model smaller, it starts needing to represent the regularities of the data in order to do anything at all. So capacity limitation is helpful for computation, but it's harmful for representation because it limits the degree to which you can kind of explore all these different potential areas of representational space that might be useful for then performing computation with. So as far as I know, forward self models are really the only thing that I know of that dissociates these conditions of being able to compress just the computation while inheriting the representations of the main model. I think this explains both the parameter efficiency of the forward self models. You're learning a compressed basis with a dramatically smaller number of parameters in some case than even the intervening layers of the main model that you're modeling, as well as the interpretability of the residuals. Insofar as if we are modeling the computation directly, you would expect that to have interpretable results. And I think that's pretty exciting. So I think this has applications for both mechanistic interpretability and for potential future architectures here. It may not be that forward self models produce interpretable features in the sense that we're maybe used to in mechanistic interpretability. They're not producing like explanations of what the model was thinking in natural language, like something like natural language autoencoders might do. They're not telling you something about the model in English. What they're doing is they're telling you something about the main model's computation in the language of the main model itself, which is ultimately the activations that each layer then acts upon. I think we've shown that this has automatic decomposition along the architecturally meaningful boundaries of the main model. So you can sort of get a sense of what matters between the MLP and the attention heads in the transformer. That's potentially a really interesting takeaway from this. And ultimately, I don't think this is a replacement for anything in the mechanistic interpretability suite that we already have. This is just a new way of compressing computation that I think probably could work well with existing mechanistic interpretability techniques. And going forward, I'm really excited about this as a potential primitive for some kind of exciting ideas that we don't have great ways of representing in ML right now, specifically along the lines of self-monitoring, metacognition, adaptive computation, that sort of thing. If you think about it, like one of the things that LLMs right now are not great at doing is, I would argue, specifically what is known in psychology as metacognition, the ability to think about your own thoughts as an explicit object. And that is kind of what the forward self models are, right? It's an ability, it's a model that meta models the first model. And if you give the outputs of the meta model to the model itself, that's kind of a form of metacognition almost by definition. It learns what the main model is doing. And interestingly, because the main model's computation tends to be like smeared across layers in some sense, that like no layer exists in a vacuum, that like it only does one sort of computational function. There's a sense in which forward self models, even when they're modeling only just one layer or a small group of layers in the middle of the network, I think they're really learning something potentially more fundamental about the model as a whole and what the entire process of computation looks like for the main model. So that's one of the reasons that I'm excited about where this goes, and I'm excited to tell you more about what I've been working on. So that's all. Hopefully I will continue to make more videos about this. I'm excited to tell you about what I'm working on. If you want to learn more or play around with this, the GitHub link is on the screen. I've made the code all open source on GitHub, and the model checkpoints are available on Hugging Face. So you don't even have to retrain anything, although it's pretty cheap if you want to. You can go and download this, do ablations, try out new methods of inducing generalization using the forward model, whatever may come to mind. Please do send that to me, and I'm excited to see where you take it. Thanks a lot, and hope to see you soon. Take care.